welcome to already the fourth day of this school on QCD. So we were discussing in the previous lecture, in the first lectures, having looked at more general aspects of gauge theory. In the previous lecture, we've been looking at things you get when you do loop integrals, the problems, particularly UV divergences that you find, and how to first of all categorize them and to make them manageable through a regularization procedure. And we went in some detail through dimensional regularization. And then we discussed how to cancel these divergences through renormalizing the fields, the couplings, the masses, which led to counter terms, which you could choose such that these divergences are cancelled. And the magic of renormalization is that it works then for all other one-loop diagrams too. Besides that, there were also some consequences for the theory. You need to derive the beta function equation. So we noticed that as a result of the renormalization procedure, you can introduce some arbitrariness, which at first seems a problem, into the story. But actually, we found that this arbitrariness can be used to compute the energy scale dependence of the coupling. Coupling is not a constant number. We found, for example, for the QED coupling, this general form, in fact, that always holds for any coupling if you renormalize, but we computed also the first term, which is positive, and that meant that the coupling rises as a function of the scale. And I told you, rather than derived for you, the fact that in QCD as a non-abelian gauge theory, and non-abelian gauges are unique in that sense, that for QCD, the beta function is a negative. And then you get this dependence, which we know as asymptotic freedom. And I told you that I told you the first term, and in fact it's now known to 5 terms. And the higher order terms change the result a little bit, decreasingly so. The fourth order term is less important than the third, etc. So exactly as you would hope and expect. And it stays negative. So asymptotic freedom, which we think solves this problem of confinement versus free particles in the Parton model, is really a feature that is true to all orders. What I'd like to do today is to discuss this a little bit more, also a bit the meaning of this, a particular physical picture you can have around this. I'll not just discuss the beta function. I'll start with discussing a bit another function that comes in, analogous to the beta function, called the anomalous dimension. That is also a quantity that occurs a lot in quantum field theory and of course also in QCD. And I'd like to discuss that a little bit in conjunction with the renormalization group, RG. Also a tool that occurs all the time. When we finish that, for the rest of the day, I'd like to discuss not the ultraviolet but the infrared sector of the theory, and that will occupy us more or less for the rest of the course. That's more complicated, but also that's really where the interesting difficulties of QCD and also the very interesting structures of QCD really come to the fore. So let's first have a look at the anomalous dimensions. Now, how do they occur, and what are they? Now, we saw that the beta function follows essentially from the rule that this is equal to the renormalized coupling. Okay, there's some scale here, and then Z, E, which depends on the divergences and the coupling. And this is a self-consistent equation. We acted with mu to d mu, and we got an evolution equation for the coupling. Following essentially from the Z factor for the coupling. Anything I should? Okay, thanks. So let's look at a Green's function, an endpoint Green's function. And for the moment, let's ignore QED. Let's make it easy. Some scalar theory, just to illustrate the point. Endpoint Green's function. Now, in quantum field theory, this is defined. So here is our Green's function, which depends on some momenta and a coupling, all bare. So we put a 0. No renormalization yet. And the general form, I just want to give you the form that motivates what comes afterwards, is a Green's function is always a time-ordered product of a field at x1, and since we have an endpoint Green's function at xn, and I put a 0 here to indicate it's a bare field. And this is in coordinate space, so we have to do also all the Fourier transforms to momentum space. So in quantum field theory, this is what you learn. You take a time-ordered product of a number of fields, and that gives you, well, a blob with n lines sticking out, and that leads to lots of diagrams. If you have 2 lines here, 2 fields here, that's called a propagator. It doesn't really matter if you've never seen this before, then take it as given. But one thing to observe is that there are n fields here. In the path integral, by the way, this is not with operators, but then this is downstairs, and this is, you put the path integral around. There's different ways of seeing it. Anyway, there are n fields there. So again, this does not depend on anything like mu. It's a quantity pre-renormalization. So now we normalize. That means that everywhere you see quantity there that should renormalize, you should do it. So G0 should be GR of mu. I ignore the scales, explicit mu to the epsilons. They will just go along, they will be properly accounted for. Times ZG, 1 over epsilon GR of mu. That's the coupling renormalization for this theory. And we have also the field renormalization. Phi 0 is the square root of Z phi times phi are renormalized. And this also depends on the renormalized coupling. You can imagine that we've computed these Z factors to some order in perturbation theory from self-energy diagrams and vertex correction diagrams, as we did for QED, or someone even better, someone has done it for us, and we trust that person, or it's in a good book, and we take it from there. Then we don't have to work. So when you do that, well, what happens to the Green's function? Well, if there are couplings inside, that will be taken care of. But particularly, look here, you see here that each field phi 0 gets replaced by phi r and the square root of z phi. So we have that the bare Green's function of the pi's and G0 is equal to the renormalized Green's function, the function of the momenta and the renormalized coupling. But out in front sits Z phi to the power n over 2. And there may well also be here explicit mu dependence from a log of something over mu. And you see this immediately just from this form. Right. So we have here an equation that is now for a Green's function similar to this equation. And let's see what we now get. Can we get a consistent equation for? I'll just erase this. You had this already yesterday. Sorry? G0, that sits, you see always implicitly in this you have to think of the interaction Lagrangian. That's is it the so-called interaction picture, if you know a little bit of field theory. So you have e to the I s interaction part of Lagrangian, which contains a coupling. So in such a thing, See, if you had if you didn't have it, it would be a free field theory. So you always think implicitly that's inside. Not the prefactor, it happens inside. Yeah, yeah. So if you act now with mu to mu, then you get again 0 on the left hand side, and this is equal to, again it's a matter of using the chain rule, so you can act on this quantity on the explicit mu dependence, on the implicit mu dependence, and there will be also mu dependence inside the z factor here. So you get the explicit dependence, so we write a partial derivative there. Then we have the implicit dependent in the coupling, and then ddg on what comes afterwards, and we have mu to the mu on z to the phi n over 2. But to compensate, we have this, and all of this acting on z to the n over 2 phi gamma n r. Oh, n was upstairs, r was downstairs. And this one is supposed to act only on, on all these terms, but particularly here on the GR. So this you can write as n over 2 mu dd mu on the log of z phi. And this is what is known as the anomalous dimension, gamma of phi, which is a function of GR only. And this we had already seen. This was the beta function. It depends on GR only. So we have here an equation for the, I'll just copy it down again, because it's such a standard equation. Beta of g dtg plus n over 2 gamma phi acting on the renormalized Green's function is 0. And this is the renormalization group equation. So it tells you how, when you change mu, not just how the coupling responds, that's what the beta function equation does, but it also tells you, this equation tells you how the Green's function as a whole responds, either implicitly through the coupling, or in a sense through its normalization, through the renormalization of the fields that make up the Green's function.
The renormalized Green function does not depend on a scale.
Sorry?
Renormalized Green function that we observable in the experiments does not explicitly depend on a scale.
You don't observe Green's function in experiments. In order to make experiments, you have to relate Green's function experiment. You have to do something called the truncation, etc. And then you get that the thing depends implicitly not on the scale, only through explicit and G dependences, RG invariance. But for Green's functions, you have an anomalous dimension. So in some sense, the anomalous dimension, I'll say a bit more about it in a few minutes, tells you how the normalization of the Green's function responds when you change the scale. It's an important quantity, so beta functions and anomalous dimensions really elements in RG equations, and whenever you encounter in quantum field theory an RG equation, then you have to think, is there an anomalous dimension? And if so, what is it? Yeah?
In that equation, Z phi will be there. Z phi to the n by 2.
No, that drops out. It's not acted on anymore. That's why I divided it out. So, sorry. This is partial loop. This only acts through. This acts straight on the Green's function, and this acts the acting whatever happens in here sits in the anomalous dimension. So we'll see a few more. We see the meaning of this, and we solve this equation also in a more general sense in a little bit. At least you've seen the definition. As you see, it is quite similar to the beta function, except now a different z factor. Now let me return a little bit to the beta function and give a bit of a physical picture. So it's some physical intuition about the running coupling. At least in QED, and QCD will then be analogous to it. So in QED, we had seen there were 4 diagrams, but as I told you, coupling renormalization only results from this diagram, the self-energy in the external photon. There were 3 other diagrams, but their UV divergent parts cancel among each other. So, okay, so let's just keep that a little bit in mind. Now imagine the following physical situation. You have vacuum, completely empty in principle. We suppress quantum mechanics in some way by some kind of magic. And we put a positive charge in the vacuum. And we know what kind of electric field that has. It has a radial electric field. Now how would you measure the charge in that situation? As a theorist, you would put a kind of sphere of some radius r around that point, and then use Gauss's theorem. So you measure the charge, the surface integral, which I always like to draw that symbol. It's one of the first symbols I saw. I really was intrigued by that when I was younger. So you do surface integral with this, and well, the charge is 1 over epsilon 0 times the enclosed charge, right? So that's how you would measure it, and we all know from E&M that it doesn't matter how far you pick r, the fall up of the electric field precisely compensate the growth of the surface such that you just get Q of r, a number. It's always the same number. But the vacuum, we now turn quantum mechanics back on. So the vacuum is full of virtual fluctuations. Particularly, you could have a photon briefly forming an E plus E minus pair and then disappearing again, or any other fermion pair. But let's stick with electrons. They're nice and light. Lighter particles are more easily temporarily created and then disappear again. Very heavy particles occur much more rare. They have to go. The fluctuation has to go much further because of their mass. It has to go much further off the mass shell. So the vacuum is not empty. In fact, we have lots of dipoles around. So we have where to draw it. I'll do it here. This can be seen well. So we have here our charge, but if the vacuum has lots of dipoles, these little temporal fluctuations, they will align themselves such that they turn the negative side towards the charge that's already there. Minus plus, minus plus, minus plus, etc. And those dipoles generate electric field back towards charge. Right? That is fairly obvious. So the electric field that will now, in the presence of this medium, the polarizable medium, will occur, will be falling off faster than if it was just an empty vacuum. So electric field of dipoles screens the original E. And if you now draw a surface, we'll go partly through these dipoles at some distance r, then you will find that the full electric field will be 1 over epsilon times distance dependent charge. The extra weakening, because it was critical, 1 over r squared, a bit of weakening of the field will offset the r cancellation. So you will get an r dependence. Now it's also fairly clear what this means. This charge is screened. It looks less than it would be if there was no vacuum field. So it means that if you would go to larger radius, then the charge gets smaller. If I look further away, I see less of a charge than if I look closer. There was more screening happening the further away, more dipoles are in my Gaussian surface, so the charge will be smaller. In other words, if you say, well, corresponding to looking further away means to lower scales. So this is equivalent to Q. So Q goes like 1 over R, goes down. So you see indeed that the Q goes down, the typical distance you look at. If that's less, then the charge will drop as well, and the same thing the other way around. So you typically will find the behavior where, as a function of Q, I used too much Q here. I should have used E here. The charge, and here as well. Right, so I find precisely the behavior that the field theory also tells me. And you also see it actually fits the field theory a little bit. The story of the dipoles fits the one diagram that contributes. It's a bit of not quite a coincidence, but it's a nice correspondence. You see indeed these little dipoles here appear. That's QED, so we can have a good understanding of why the charge behaves the way it does as a function of the scale. Now we have a physical picture that we can have in mind. For QCD, the opposite happens. So an anti-screening. Now that is very difficult to visualize. Lots of directions you have to keep in mind, such that I will not attempt it, because if I attempt it, I will just confuse you more. Somehow it is that there, if you it's a bit like magnetism. If you magnet a magnetizable medium, the magnets help to amplify the field rather than screen it. So it's a bit of a magnetic phenomenon almost. So that's a bit of gives you a bit of a sense of how to think about the running coupling. Sorry? No, I don't think repulsion. No, it's you can think of this as a static situation. Okay, so that gives a bit of a meaning to this scale mu, at least as far as the running coupling is concerned. Now, I haven't told you yet about what to choose for mu. And so far I've said only mu is arbitrary. It's one of these byproducts, some arbitrariness that is logically there in the renormalization procedure, and if it's logically there, you have no reason to suppress it. So the you cannot just because you don't like it not think about it and include it. So it is there in our calculations. Its arbitrariness must be accounted for. But still, if it's arbitrary, we do a particular calculation, we work hard. In our final answer, after we renormalize and do everything we need to for our physical prediction, things are finite, but there's still mu dependence, either explicit in some logarithm or implicit through the running coupling. And we have to then make a choice. If we want to use a calculation to produce numbers for an experiment, then we must make a choice. And the question is, what is a good choice? So what to do with mu in a calculation? And this is certainly the topic of ongoing debate, not so much in principle, but in very complex calculations. It is also not an obvious thing to choose, but let's keep it here a bit simple. Now, there are such a thing as typical energy scales for observables, for observables O. Let's give a few examples. So TT bar production, which we already discussed. The typical energy scale when you do TT bar production would be, let's call that energy scale Q again, is the mass at the top. That would be a good choice. It's not necessarily the only choice. You could also think of the mass of top and antitop, or the invariant mass at the top there, but this is a typical choice. Certainly the mass of the electron seems to be not typical. We have no good reason to reject it, but this at least is a scale that naturally occurs in this process. For Higgs production, the typical scale would be MH. But not necessarily. Suppose you do the differential distribution for Higgs production in the transverse momentum of the Higgs. So suppose typically that will look like this, and d sigma dpt h. The typical form will be like this, and this is a logarithmic scale, so that here this is more or less pt. But if you look at these bins, perhaps this is much larger than the mass of the Higgs. Perhaps the typical scale is the transverse momentum of the Higgs, which could be 4 or 5 times the Higgs mass. That could be a typical scale. Anyway, just to show that there are options. And if you have jet production at a certain, when the jet comes out with a certain PT, that typically would be the scale involved. That would be the typical scale involved. Okay, but this is just a bit of feeling. Let's see if we can make it a bit more concrete. So after renormalization, an observable will have the typical formula. Observable will have the expression O, the O is the observable, equals gr squared of mu. So we have everything is renormalized, so our coupling is renormalized and dependent on g times. And if we only had done the leading order calculation, we would have something here, some numbers or a function with this strength to coupling, say, and that would be it. But we saw already in TT bar production, the coupling comes out in front. That's it. But if we do a next to leading order calculation, that means we have g to the 4th contribution. Then there are typically 2 classes of terms there. No matter how long the calculation is, sometimes millions of terms. But there are 2 classes. There's terms that have an explicit logarithm of q over mu. And there are those that don't. And such an explicit logarithm comes, for example, if you remember, if you have your 1 over epsilons and say some, say you have some mu to the epsilon, and maybe you have a q in the minus epsilon as well, all of that can come in dimensional regularization. And we certainly saw the mu to the epsilon before. You can write this as q over mu to the power minus epsilon, which is 1 minus epsilon log of q over mu plus order epsilon squared. We had seen that before. As you get these things with the power epsilon, you can make into series and epsilons through this very simple trick. And if you then combine this epsilon with this 1 over epsilon, you have a log left. Never more than one log, because we only have maximally one pole and one loop. Right? So at 2 loops, you can now guess gr to the 6th. You have now 3 types of terms. Those with 2 logs, those with 1 log, and those with 0 logs. So you have O20 plus O21 log q over mu plus, oh sorry, I'm running out of 2 log squared q over mu. But you see the pattern, it's not divided by, it's just r. So you see the pattern occurring, and this is very general, right? From what we have discussed, you can understand this. I haven't told you what these O's are. Those will be typically very dependent on whatever reaction we're looking at, but that's the structure. Now that we have this, now we can sort of make a reasonable judgment about what is a good scale of mu. Also keeping in mind that this pattern continues. Suppose a Q is the top mass, and you choose, you say, well, I like mu to take the electron mass, or the neutrino mass, 10 to the minus 11. Right? Now what is the consequence? This will have some number. In fact, if it's QCD, it will be it will be a problem anyway. But let's look at these explicit logarithms. So if this ratio is hugely different from 1, the log will be very large. And it will occur systematically more and more powers at higher order. In fact, you see you have a g to the 4th times the log, you will have a g to the 6th log squared. So slowly some kind of perturbation in g squared log q over mu is emerging. If you look at the highest power of the logs, the last term in these brackets. And if this is small, but this is very large, because you took such a bad scale for mu, you don't have guarantee for conversions anymore. So a reasonable choice is to take mu of order q. You don't have to choose mu equal to q. Right? That is not necessary. That's nice, then all the logs disappear, and often that is what's done. But if you take it 2q or even 5q, that would not be too bad. The logarithm of 5 is not a large number. All you have to do is avoid this becoming too large. Right? Does that make sense? I think this really gives as solid as possible a reasoning for what you should choose from mu.
I mean, it's not meant to depend on mu though, right? Your calculation. Eventually the mu's should cancel out each other.
If you could do all order calculations. But we always have finite energy and strength in life. So there's always terms you don't know. And what you'd like to know is that the unknown terms are small. So to every finite order you could work, you want that the remaining ones are very, very small. And if you make a very bad choice, you have no guarantee for that. In fact, it will look even worse. There is another, I'll make that remark only in words, aspect that these series actually never converge. The so-called asymptotic series. That terms that get smaller and smaller and smaller, at some point become larger and larger and larger again. That doesn't mean that they're infinite, weirdly. You can define them by stopping summation at the moment when they get smallest. So this argument that to all orders the mu dependence should vanish is also a little bit subject to that caveat. But this is, I think, a fairly solid argument that is worthwhile seeing. So what do people do in practice? Let me go here. See, it would be not good if you were so happy with this argument that you say, okay, I'll choose it to be Q or 2Q and I'm done. So I won't even say a recipe, custom is to choose mu equal to mu naught, which is of order Q. It could be Q itself or a little bit different. Then vary mu around between mu 0 over 2 and 2 mu 0. So you pick your value of mu 0 and vary it between those two values. Why 2? Convention. There's no good reason. 3, some to people 5. This is somehow has emerged as a convention. What you then get is if you have a kind of prediction for some, say the top sigma tt bar as a function of the top mass, you get something like this. Sorry, it goes down. As a function of the square root of the collider energy. So this would be for the choice mu is equal to mt, and if you then vary to mu is a half mt, and here mu is 2 mt, you get a bit of an uncertainty band. It's a way of estimating a theoretical uncertainty in your predictions. Experimenters can't do perfect measurements, and we cannot do perfect calculations. So we have to be honest about as honest as we can about the uncertainties in our calculations, and varying mu around the typical energy scale by a factor of 2 is very customary. Okay? And there's debates about 2, and is this good enough, or is this not too small? These are very interesting debates always, and there won't ever be an answer, or everyone agrees upon. But it's good to be aware of this.
Experimentally, what does this mu then refer to? What do you control? I mean,
well, it's a theoretical parameter. You cannot. The thing would absolutely be wrong to do. Never do that. Let me repeat: never do that. Is to, because it has been done in the past, about 20 years ago, by some experiments at lab, which is not a good idea. To use the comparison of theory today to fit what mu is. That you should never do. So you should judge what the typical energy scale is as a theorist, and vary around that by a factor of 2. As I said, to see what typical energy scale is not a particular difficult thing to do. Except, suppose, for such things, suppose you do 5 jets plus 2W production. All the 5 jets have different kind of transverse momenta. You have the W mass, your W's have PT. Certainly you have a situation with a very complicated final state with lots of scales. This is when the interesting debate also happens. What do you choose then? The sum of all these scales, or the lowest one, or the average? What do you do? That's not so clear. There's not an a priori answer. Okay, so this is what I wanted to say about the scale choice. I'd like to return a bit to the renormalization group equation. And to solve it. And particularly, I would like to show how you can resum. and I'll tell you a little bit what I mean by that via the RG equation. Resummation will be a bit of a theme of the lectures next week, and we'll see all kinds of methods to do that. This is summing things to all orders of perturbation theory, and solving the RG equation will be one method in which you can do that. Some collaborations and ways of resumming really rely fully on that, such as soft collinear effective theory. So it's worthwhile addressing this a bit. And I'll do this in two ways, in a bit of a formal way and a bit of a quicker way, both more or less giving the same result. But let's see how it goes. We had seen, so what kind of resummation are we thinking of? We saw already actually resummation for the coupling. I'll just make that remark here. We had the QED coupling, and we had that the running coupling at some high scale mu, and you've actually solved this in the tutorial, was equal to 1 minus EI squared log mu Q0 1 over 6 pi squared. Right? This is actually a resummation, because this right-hand expression is all orders in the coupling EI. That is the renormalized electromagnetic coupling at the low scale Q0. So EI initial is ER evaluated at Q0, the initial point of evaluation. Because I can expand this in EI and build a series to all orders. And the higher power of EI, together you will get higher powers of this logarithm. So by solving the evolution equation for the running coupling, really, which is in sort of RG equation itself, I've created an all order form.
Without calculating the loops, details of the loops.
Sorry?
Without calculating full details of the loops.
I've got only done a one loop calculation.
Yeah, but you can able to speculate the evolution of the coupling constant in all orders.
Yes, so that would be in higher order terms in the beta function.
Yeah, but you explicitly haven't calculated by loops.
No, I've done a one loop calculation that gave me the beta function, and the beta function equation, solving that, gave me the all order expression.
But in beta function there might be a higher contribution. Huh?
You could do, as I said, in QCD we know to 5 orders, and then the forms will be a bit more complicated than this. You can still do it. So by solving an RG equation, we have created an all order expression. We've resummed to all orders, at least the logarithmic terms. And you can do something similar through the RG equation, not for the coupling, but for Green's function. So, so here we have one equation for the Green's function. Let's repeat it. The explicit derivative. And this is a bit of a perhaps a slightly tricky argument. It will be in the notes that will be handed out today. In section, I think 5.4, working on the endpoint Green's function. So that equation we have, that's the RG equation. Right, for a given Green's function. Think 5 to the 4th, for example. I'll just write it so, a 4-point function with all kinds of loops in, for example. So that's 2 to 2 scattering. You could think of other Green's functions too. It's quite general. Now we can write a second equation. So this is now a way of solving the Green's function and make it a bit more explicit. It also gives you another picture again of what this mu could be, of what this mu means. We can write a second equation. A so-called homogeneity equation. If this will be a bit tough, there will be a simpler version right afterwards. So you won't miss anything really crucial. A homogeneity equation. And that one we derive as follows. So if you dimensionful parameters are in such a Green's function are the momenta and the scale. So are the pi and mu. If I rescale those with lambda, I will get that gamma of lambda pi, the coupling lambda mu, will be, well, this thing will have some dimension. If it's 5 to the 4th, it will have dimension 4. It will be lambda to some power d gamma times the thing with unscaled momenta. Vg mu. This must be so. Even if it's a sum of terms, they all will have the same dimension.
That d should be equal to the anomalous.
It's not the anomalous dimension. It's the canonical dimension. It'll come later. Yeah. So each term here will have the same dimension, 4, so no matter how complicated, and I can only make that through the pi's and the mu. So if I scale them all uniformly, each term will have such a factor in front. Right? This is just scaling. I'm not saying anything particularly deep. Now what you can do is take lambda near 1. So do just a little bit of scaling, almost imperceptibly much. So I'll do that here. This will also be a number very close to 1. So I'll take lambda to be 1 plus, say, t. T will be very small. So that way, then I can expand in t. And on left and right hand side there will be a gamma left. This will also be 1 plus something in t. This will be 1 plus something in t, and then I can remove the 1 terms. And what you get, and you will see this also in the notes, is, let me do it here. You get mu dt mu plus d dt acting on gamma of n e into t pi g mu is 0. So roughly here is what happened. So when you vary lambda here on the left, sorry, it's not 0, it's d gamma times gamma of n. So the right hand side is certainly easy to see. If you have lambda to the power d gamma, the canonical dimension, the usual dimension of the Green's function, then lambda is 1 plus t. If I raise that to the power d gamma, and I take a small t limit, then this will be 1 plus dgt, right, plus order t squared. The 1 was dropped on both sides of the equation, and leaving only d gamma, the t will also be dropped. So that explains the right hand side. Is that clear? The left hand side, well, this way of writing it is just to show that I'm varying mu a little bit and I'm varying the momenta a little bit. If I act with mu dt mu, the explicit derivative, I only act here. So this is tiny variation in mu. That is from this particular variation. And ddt only acts in the first coordinate here, because that's the only place that it's present. So this derivative just varies this a little bit. So this is a bit of a clever way of writing that I'm both varying the first argument and the last argument, as I do here. Right, so that's more the infinitesimal version of this scaling equation.
How this one cancels?
Oh, because lambda is very close to 1. So if I expand this, the leading order term will be gamma of p, g, and mu. And on the right hand side too. Yeah. And this also has to be expanded. So what can I do with this? Well, I can use this equation to trade the mu dependence for DDT dependence. And the nice thing of DDT dependence is it really directly tells you how the momenta are scaled. Here mu is a bit abstract, and this way I can relate it to scaling the momenta. So I get the equation trade mu to d mu for ddt in the RG equation, and that gives ddt minus beta of g ddg minus d gamma plus n over 2 gamma phi, they call it gamma phi, of g on the renormalized on the Green's function itself, e to the t pi g and mu. So now the differential equation is a bit more clear what it looks like. It says, well, if you scale the momenta coming in and out of the Green's function, how does the Green's function respond? Well, by changing the coupling a little bit, and by changing its dimension a little bit by an anomalous bit. This is the canonical dimension, this is the anomalous dimension. Right? So how can you solve this? That's also in the notes. I will not go through it now, but I'll give you the solution and you can read up on it in the notes. Sorry? Well, as I said, so this says if I change the momenta a little bit by varying t here, and t only occurs multiplying the momenta. So varying those, this is what this means. How does the Green's, this is equal to 0, sorry. How must the Green's function respond? Well, by changing its either the scale in the coupling and also the way it scales as a whole. So to the regular scaling dimension and the anomalous scaling dimension.
What do these dimensions actually mean? Like the anomalous dimension, what does that mean? Does that have physical meaning?
Well, this is what I'm saying. So normally if you have such a Green's function, you have dimension 4. That's true at tree level. If you do loops, they get little correction. At least in the context of these equations. And that's also the setting in which such dimensions matter. So not only does the coupling no longer is a constant, it gets a little, starts varying a little bit, the dimension is no longer a constant. It starts getting corrections too, and that's change. So all of this is a consequence of loop effects.
If you have a theory such that anomalous dimension is 0, then you can say that the theory is invariant under the scale transformation.
Then you have a scale invariant theory. Or you have an object which has no intrinsics, which has no anomaly, which has been normalized such that there is no anomalous dimension. So,
after renormalization, you must have got a scale.
After renormalization, you must have
Got a scale.
Well, even before, but after renormalization, you have the scale mu. Yeah.
Okay, so you cannot have a renormalized quantum field theory that is scaling invariant.
Yes, you can.
Okay.
N equals 4 Yang-Mills theory is scale invariant. Yeah. It has a beta function that's 0.
Yes, the function is finite, then
That's, I don't know if that's a theorem. I'll have to think about that. But and this takes us a bit to realms that you're not discussing.
finite, then consider that the function is 0.
Zero is finite. You don't have to renormalize.
Yeah.
Then there is no beta function.
But if the theory is not finite, but that means in that case, like, could we have that beta function is 0? The theory is not finite, but beta function is 0.
Yeah, you have. So for n equals 4 Yang-Mills theory, you have to renormalize and the beta function 0.
They are infinite in the without renormalization, they are infinite.
Yes, but after renormalization, you can have still that beta function is 0. That's right. So now how to solve it? As I said, that will be in the notes. Let me just write down the solution. It's a 2 or 3 line method, not difficult at all. So the solution is that the Green's function with rescaled momenta, so for some value of t which gives a different value to the first entrance than just the pi's themselves, g mu is equal to gamma of n, the unscaled momenta, but now the running coupling must be evaluated at scale t, and you think of t like log of mu squared, log of mu. And mu times the exponent, integral from 0 to t dt prime let me call this combination here d gamma tilde, meaning it contains the regular dimension, the canonical scaling dimension, plus the anomalous dimension as a function of the running coupling. Notice again the exponent. So this is a series, an all-order series in G. Right, by having solved the RG equation, also here we have found a resummed expression, just like we did for the running coupling. Now for the Green's function. So this is a resummation. Now in exponential form, and that is a very common form. Sorry? So inside here, this is a function itself of G, and you can expand this in G in the exponent, and then expand the exponent, and do all the integrals. You will certainly get an all-ordered expression. I haven't told you what it is, but just to show you that once you have things in an exponent, it's of course all orders, because the order counting only counts downstairs.
What is the relation between t and mu?
Yeah, it's they're more or less related in this way. The real definition is that ddt of g of t is the beta function of g and t. So it's solving the same equation. So this is a bit of an involved argument. I'd like to do it once more, now quicker. But this way of doing it really relates a bit the meaning of the RG equation and the anomalous dimension. If you rescale the external momenta, how do you know what the Green's function is at rescale momenta? Well, the RG equations, it's fairly easy. If you know your Green's function with unrescaled momenta, take that, substitute the solution to the beta function equation, and multiply by this factor, which you can also compute. So if you do a low energy experiment and you've done a calculation for that, then to compare with. So you fixed it and you checked that it works. Then you have this thing with a G. The instruction is if you want to do what is the same Green's function relevant for a similar experiment but a much higher energy, well, that would be what you want here. The instruction is, well, take your low energy thing, replace it with a solution to the running coupling equation and multiply by this factor. And that will be your prediction for the same Green's function with much higher momenta coming in and out. Okay? So what looked like a problem having this arbitrariness, this mu dependence in as a result of renormalization has a lot of benefits. It gives predictive power how strong the coupling becomes or how weak the coupling becomes. So it allows you to do experiments like deep elastic scattering, allows you to do perturbation theory with QCD, all that for the coupling. But even beyond that, you can even for whole Green's functions use the RG equation to have predictive power. To say if I know at a low scale, I know what it will be at a high scale. Can I take 5 more minutes for finishing this argument, doing it again, but then quicker, without the T parameter? And it's the way it's most often presented, but this is a bit of a different way that I just showed. So a quicker way. It doesn't get exactly the same equation, but it gets you similar information. And it lets you then to think about how exactly the two are related. So again, we have our unrenormalized Green's function. And we have that the thing is renormalized as follows. With a 1 over epsilon, gr of mu, and then in here, gamma n. And this is a quite elegant form too. And maybe mu dependent, explicit mu dependence also. Okay, so this we have written down before. Now look at this from a different point of view. So we have here a bare Green's function where we just had diagrams and we get all kinds of stuff out, including 1 over epsilons. What we have said here, well, this can be written as a finite Green's function after renormalization times factors with infinities in them. So all the 1 over epsilons are in the overall z factor. Inside things that cancel, that's renormalized. Here we have separated, factorized the UV modes from the non-UV modes. So this gives you UV modes, give the divergences, and these are the ordinary modes. This is a factorization of UV modes and normal modes, meaning not UV. Modes means typical momenta, typical when you have the typical energies involved after doing all the integrals. Okay, so these will be finite functions, and here we have 1 over epsilon. And there is a very general statement that factorization of any type implies resummation of the type we have seen here. We had seen that for the case of the electromagnetic coupling. We wrote the bare coupling is equal to E, the renormalized coupling times the Z factor. Also that is a factorization. Acting with mu to d mu gave us a evolution equation for the running coupling, the beta function equation, solved it, and we got this all order form. And it also works here. So so take logarithm, take ln, act with mu to d mu. Those 2 steps, And then we get the following equation, that minus n over 2 mu dd mu on the log of the phi with 1 over epsilon. I make a point of writing the arguments here, equals mu dd mu on the log of the renormalized Green's function pi gr mu mu. So if I take the logarithm and then execute the mu, I get 0 here. And I get these terms, but this I bring to the left-hand side. So we get minus n over 2 times this is equal to mu dd mu on the logarithm there. Okay. Now, this is actually very nice, because I like to know an equation for this thing, the logarithm, d mu of the logarithm of the Green's function. But on the other side, that seems to be some kind of logarithm of z with one of the epsilons inside. Doesn't seem particularly useful. But the left-hand side, I will call n over 2, again, the anomalous dimension. And what can it depend on? I'll call it already the anomalous dimension even before I have made the argument. So I'll make the argument now. Because it will be the same as the RG equation. So I call this gamma, the left-hand side is minus this. Now, what can it depend on? That function gamma of phi. It's supposed to only depend on gr of mu, and that's really the only thing it can depend on by separation of variables. You see, left-hand side I have 1 over epsilon and gr. On the right-hand side I have momenta, gr and mu. The only common variable is gr of mu. So by the very elegant argument of separation of variables, this thing is only a function of gr of mu. And we had seen already in the previous story that this is nothing but g of phi. But I've argued now from a different reason that you can directly get it from z phi. And also you know now for sure that the argument is only gr of mu and not 1 over epsilon inside or so. So I can now solve this. Mu dd mu of the log of the function equals something that is easily solved. So now we get, and now it's in the form not the momenta are we scale, but mu of g r of mu, or the pi g r of mu equals, let me rewrite that, it's a bit messy. Gamma n renormalized as a function of pi gr of mu and mu equals the semi-normalized Green's function at a low scale, so pi gr of q0 times e in the power from q0 to q to mu d mu prime over mu prime n over 2 gamma mu of gr of mu prime. Oh, yeah, so let me stand here, otherwise the board is not shown. Okay. So, again, very similar solution. You know the Green's function at a low scale, but we leave the momenta here intact to, you know what to do once you have this to get the Green's function at the high scale mu, if you know the anomalous dimensions. And now it derives in a much quicker way. So this is all a bit tricky stuff, I realize. But I did want to discuss it because it is such an integral part of the whole story of renormalization. And it has real benefits in that it allows you to construct all order expressions for the basic quantities of the theory, the coupling, You also have a running mass if you wish. You can also compute all order forms of the Green's functions. If you know at one scale, you can compute, thanks to the renormalization group equation, what they are at high scales. That's all I wanted to say about this. Are there any questions?
To get ordered result, you should know about this anomalous dimension of the sufficient order.
That's right. You must know at least what it is. If you've not computed it, it stays a formula without having something to actually compute. But if you've done a one loop calculation, then you know what gamma phi is to one loop. Also, these anomalous dimensions are known now for QCD to 4 loops. So, and other theories as well. So it is not a free lunch. You don't get anything without calculating loops. But if you compute even one loop, you get an all-order result. If you get 2 loops, you get a better all-order result. If you get 3 loops, an even better all-order result. We'll come a bit what better precisely means later in the course.
That means like the complicacy which stays in Green's function is less this complicacy to calculate this anomalous dimension may be less than this Green's function.
That's right. That's right. If you want to, of course, you can't get the exact answer at a high order, but you can get a lot of the logarithmic terms there that you would get from the low scale. So it is a real efficient way, often a very accurate way of getting high order results. In a different setting, people have used such formula to predict what you get at high orders. For example, suppose you know this to one loop and gamma phi to one loop, then you can expand this exponential to the next order. And if you then later, or even before, have done actually the 2-loop calculation, then you can see, okay, how good is the comparison between the real full 2-loop calculation and the one loop dressed up with some extra logarithmic term from the Archie equation. And often that is really quite good. Not always, but and many times it is very good. And it's also understood then why it is good. So it has that aspect too. It can help you already get higher order terms. But it does not completely remove the need for any higher order calculations. Yeah? So this is also a bit of exercise into looking at such an expression, and of course it looks very mysterious, but at least to recognize that this is in principle an all-order expression. Never mind that you cannot immediately sit down and give me all the terms that occur, but the fact that it is a function of the coupling sitting in the exponent, that alone says all orders. Because I can expand this in G, and we'll get a series to all orders in G. Okay, this is not an easy bit, but it requires also some thinking and maybe reading in the notes. So maybe it's good to have a break now.
Test to be based on whatever is done till today and the lecture notes. You can use the lecture notes and simple test. It's supposed to be a 1 credit course, so if people don't want, we don't have it. But how many people need the credit? You'll get a certificate of participation. And then if you appear for test, you also get a grade card. We can just make it satisfactory, unsatisfactory, just 2 grades. Instead of having a ABC 3 scale, you can just have a unsatisfactory and satisfactory.
I'm fine with that. It depends also what the GEON network wants. But they have their requirements too. But I'm happy with whatever.
We'll keep it as simple as possible. Just try to go through the notes and whatever problems are given till today, whatever discussed in the class. Don't expect
require that some kind of test is given. Right?
They wanted evaluation.
Yeah.
So we thought of giving you a test. Can use your survey. This is basically outside when we talk about continuous.